Let's look at a couple of more theorems. Each elementary row or column operation on a matrix can be affected by pre or post multiplication by the corresponding elementary matrix of an appropriate order. Now, let A be any matrix M by N and let R of A be the matrix obtained from A by an E row operation, and R I M A denote matrix obtained from I M A, identity matrix multiplied by A, by the same E row operation. Okay, then R of A is equal to R of IMA, since A is equal to IMA. When we multiply a matrix with an identity matrix, the value doesn't change. The matrix doesn't change. Now, this can be written as R of IMA. This theorem we have already seen. Instead of applying the row operation on the product, we can apply it on the prefactor in case of row operations. Right? We have already proved this. Okay, where RIM is the matrix obtained from IM by the same E row operation. Yes. So here what it basically boils down to is that this is a matrix obtained from applying a row operation. Now this A can be multiplied by the identity without any changes in the matrix. Now again, based on another theorem, which says that instead of applying an elementary row operation on a product, we can apply it on the prefactor and take the product. So that is what the theorem says. Each elementary row operation on a matrix can be affected by pre-multiplication by the corresponding elementary matrix of an appropriate order. Now, in case of column operations, we will do post. So instead of saying IM times A, we will say A times IM. And accordingly, we'll keep going forward. Okay, so that is one. Another theorem is the inverse of an elementary matrix is an elementary matrix. Okay, now here again we have multiple cases, right? So let's look at case one. Let IN be the identity matrix of order and EIJ denotes the matrix obtained by interchanging of ith and jth row of IN. Now, EIJ on this elementary matrix will give us the original back. Will give the original matrix is IN. So, which implies that EIJ times EIJ, that means applying the interchanging of rows or columns, will give us back the identity name. Okay, which implies EIJ is its own inverse. So therefore EIJ inverse is equal to EIJ. Okay, that is case one. That is the case where we are interchanging the rows or column. Okay, case 2, let EIJ denote the matrix obtained by or on multiplication of ith row of in by say lambda is the other case. So here what will happen? I times lambda is equal to lambda can be transformed into the matrix in by multiplying the ith row by 1 by lambda. Okay, so we have ei 1 by lambda times ei lambda is equal to im, which implies that ei lambda minus 1 is equal to eij of 1 by lambda. Okay, we multiply it with lambda, here we divide it. Okay, so what all this boils down to is, in case 1, what do we do? Ri exchange with rj. Okay, now if we do this again, what do we get? We get the original back. Okay, in case 2, what happens? We have ri replaced with a multiple of ri, or we multiply ri with lambda. So to get back that ri, we have to divide it by lambda. And in case 3, we have ri being replaced by ri plus lambda rj. So we have added lambda rj. So to get back the original, we subtract that minus lambda. Okay, so that is elementary operations. A couple of more theorems. That's it for now. Bye.